Welcome to another multilingual NLP session. Our first speaker is Bai Li. The title of the talk is Detecting Dementia in Mandarin Chinese.
Thank you for the introduction. Hello, everybody. My name is Bai Li from the University of Toronto, and today I'm going to talk about some of my work on detecting dementia in Mandarin Chinese. So let's get started. So let's talk about NLP for dementia detection. So Alzheimer's disease and dementia is a disease that affects around 50 million people worldwide. And one of the earliest symptoms of Alzheimer's disease is language impairment. So that NLP methods are a useful screening tool to detect Alzheimer's disease at a very early stage. And one of the common tasks to detect Alzheimer's disease using NLP is to get people to describe a picture in as much detail as possible. I will show you the picture in the next slide. And typically this gives you 1 to 2 minutes of speech. So here's a picture that we use to describe, for picture description. Given this picture, you're asked to describe this picture in as much detail as possible. And people with dementia do this task differently from people that are healthy. So, for example, they have difficulty finding words. So instead of saying the girl standing on the stool, somebody with dementia might say the girl standing on the chair because he cannot remember the word for stool. And in cases of more severe dementia, he might say the girl is standing on that thing over there. And another example is they use more pronouns. So instead of the girl is reaching for the cookie jar, they might say she's reaching for it or she's reaching up there. And they produce less complicated sentences overall. So all these features give us a lot of information about the degree of dementia that somebody has from this speech. So we use automated tools to extract features from transcripts of the speech. So first of all, we use part of speech, tag counts. So for example, number of pronouns, number of nouns, ratio between pronouns and nouns, and so on. We use features from the constituency parse tree. So stuff like max and median height of the tree gives you an idea of the complexity of the sentence. And also dependency parse tree also gives you a different view of the complexity of the sentence by looking at the dependency distance. So the data set we use, first of all in English, we use a data set called Dementia Bank, which contains around 500 picture description samples. Around half of them are from healthy patients and half of them are from people with dementia. And for Mandarin, we use the Lu corpus, which contains about 1/10 the amount, only 49 picture description samples. And for both languages, we have manual transcripts of the speech from people, from human annotators. And some previous work from a research group, Fraser 2016, extracted over 400 features on the English dataset and feeding them into a logistic regression classifier. This gives you around 81% classification accuracy. So next, we're going to talk about how to detect dementia in Chinese. And the first question is, well, why don't you just do the same thing in English? And the answer is, well, you just don't have enough data. So with English, we have around 500 samples, and with Chinese, we only have around 1/10 the amount. So if you just try to train a classifier and try to do cross-validation, you just don't have enough data to get anything meaningful. So in order to do anything, we have to use transfer learning. Somehow combine the data sets in 2 languages to get a better result than if you just use one language at a time. And of course, there are ways to do transfer learning on different languages, but we looked at some of the methods to do transfer learning, and one of the difficulties is they mostly assume that you have the same features in the source and the target domain. So this can be difficult because languages, Chinese and English, are so different from each other. So for example, here, an English speaker might say, she's standing on a chair, whereas a Chinese speaker might say something like, 她站在一个椅子上. So you can see that the word order is completely different. And not only that, if you look at the part of speech breakdown of these sentences, you see that the part of speech for these languages are very different as well. So standing in English is like a present tense continuous verb, but then in Chinese doesn't have verb tenses. Instead of tenses, it has aspect. So if you try to make a feature like the number of present tense verbs, it just doesn't generalize across the languages. So we have to try something else here. So the central idea for my paper is, instead of trying to extract the same features in all these languages, why not try to extract the features independently and then learn the correspondences from out-of-domain data? So this eliminates the need to have the same features in vastly different languages. And what out-of-domain data can we use? Well, why not movie subtitles? So here we have a corpus of movie subtitles in hundreds of movies and millions of lines of dialogue, and in 62 languages. So the reason that we use movie subtitles is that they're fairly similar to this type of speech that you encounter while doing a picture description task. So it's much more informal speech than, say, a newspaper corpus. Now let's talk about some baselines and evaluation. So we have two baselines. First of all, we have the monolingual baseline, which uses only Mandarin features. So just use Mandarin data and don't look at the English data and train a classifier. That's monolingual baseline. And second of all, we have the Google Translate baseline, which is take the Mandarin text, use machine translation, get an English text, and feed that into whatever existing classifier you have for English. So those are the two baselines. And for evaluation, we evaluate on the Spearman's correlation between the prediction of the model and the ground truth. Okay, so now we have the proposed model. So it's a little bit complicated. So let's break it down step by step. So on the top left here, you have the feature transfer model. And this model is the one that goes from a set of Mandarin features to a set of English features. And this is trained using the movie subtitles corpus. And on the right here, we have the previous work by Fraser et al. That takes in English features and then uses a logistic regression classifier and gives you a dementia diagnosis prediction. And at the bottom here, we have the evaluation. So given a new transcript of a Mandarin picture description, we extract the features in Mandarin. We feed it through the first model to get a bunch of English features that correspond to the Mandarin features. And then next, we feed it through the second model to get a prediction of how much dementia this person has. Now let's talk about the feature transfer model, which is the first part of the model here. So feature transfer model. So first, we extract a feature vector x in Chinese. And next, we extract some feature vector y in English independently from the feature extraction in Chinese. And then we learn a mapping function that goes from x to y using the out-of-domain movie subtitles corpus. And this is a multi-output regression problem. So when you have a multi-output regression problem, the most straightforward way of doing this is just train a bunch of independent linear regressions. So for each target feature, train a separate linear regression. That's the first thing we tried here. So on the left-hand side, we have the Chinese feature vector. On the right-hand side, we have the English feature vector. And for each feature in the English feature vector, we train an independent linear regression. And this sort of works okay, but the problem is some of the features are very noisy and almost impossible to reconstruct. So we have to eliminate somehow. And the way we do this is you order by R squared and only use the top K features. So what do we mean by this? So here we have the previous model, and we calculate the R squared which measures how well this feature can be reconstructed from the input features. And then we eliminate everything below a certain threshold. So if the second feature over here has only R squared of 0.1 and it's below the threshold, then it gets deleted. And this turns out to improve the results substantially. So here are the results that we have. So on top we see that we have the baselines which perform around 0.3 something, and then the initial feature transfer model does worse than the baselines, so it's not very good. But joint feature selection is effective if we do eliminate the noisy features and we're left with the more useful features that can be reconstructed. Then we get a result that significantly beats the baselines. So here we have a graph that shows the result as you vary the number of features. So at the bottom here we have K, which is the number of features that we include in a final model. And then the blue line is the Spearman's correlation, which we use as an evaluation metric. And you see that the best Spearman correlation is achieved when you have around 13 to 15 features. And then as you add more features, the blue line goes down because you're including more and more noisy features that are not very useful. And next, we perform an ablation study. So this shows you how many parallel sentences do you need to get a certain result. And we show that, and we see that we don't actually need millions and millions of parallel sentences to learn the feature correspondence. We only need around 1 to 2,000. So the size of the data that we need to do this is not particularly huge. Okay, so now let's go over what we did. So NLP has previously been applied to detect dementia in English. However, this method is difficult to just apply to Mandarin Chinese due to lack of data. And in this paper, we leverage an out-of-domain parallel corpus to detect dementia in Mandarin Chinese. And hopefully this can be generalized to other languages as well. Thank you for your time.
Okay, questions? Then I'll ask a question. So I've never worked on dementia, but I've seen the English corpus, and I think it's annotated for different levels of dementia, different stages. So the Chinese data, is it the same type of data?
The English Dementia Bank data we use as a binary score. Either you have dementia or you don't, depending on your score that you get in a cognitive test. And then the Chinese is similar. They also generate a score from. So there are no
stages of dementia there.
It's a sort of continuous variable. That's why we do. Correlation. Yeah, so the amount of dementia that you have is a continuous variable in our data set.
Yeah, there is a question here.
Hi, so I have a question about the joint feature selection. I'm curious if you've looked at specifically the features that you ruled out, and how many of those features are used by clinicians to detect dementia, to see if the features that weren't contributing much to your model are actually ones that are paid attention to or not by the clinicians.
Yeah, so that could be possible, that good features are ruled out. The way that we rule out features is not by how good they are at predicting dementia, but rather how well they are at being able to transfer between languages. So the features that we rule out are the ones that cannot be easily transferred from Chinese to English.
Right, and that makes a lot of sense. I'm just kind of curious from the clinical perspective how that aligns with what a clinician might be paying attention to when they're scoring an assessment, right? What kinds of linguistic features they might be paying attention to. So did you look at the ones that your model trimmed out with respect to the ones that clinicians might prioritize as important?
Yeah, we did. So we have a list of the top features in the paper that we didn't show in this presentation, but the features that we selected were based on features that clinicians found important, and then some of them were actually useful, and some of them were less useful. But then they were inspired by what clinicians found as well.
Thank you. I'll take a look.
We have time for more questions. No time for more questions. So I guess after the session.
Okay.
Thank you.
Thank you.